Okay, dear colleagues, I would like to tell a story about a little bit about classics and spectroscopy and these newly emerging needs, maybe press from astrophysics from one side, but also from some frequency standards as well as modern atomic physics for theoretical calculations and so on and so on. Themes we are very close to some game-changing solutions in order to get more information about classical atomic spectra for well-known atoms like usually use iodine, bromine, sulfur, arsenic, and so on. Even mercury is not mentioned there. But the problem was to get atomic spectra for hardly volatile elements like boron, copper, aluminum, and so on. And the need I already told comes from astrophysics, this after Hubble fleet of space telescopes, which are supposed to be launched in next years even. And of course, from this very high-level atomic physics with a lot of power calculations to calculate even very complicated atomic systems. And of course, there's a lot of need for various calibration sources, specific frequency standards in far ultraviolet, and also resonance fluorescence is you can have very intensive source of resonance fluorescence lines. You can use not only absorption but also resonance fluorescence for various detections. It's also some kind of come to the industry. What up to now it's very convenient and mostly used is the hollow cassette. It's well-known instruments, well-known atomic absorption instruments. And always they use hollow cathode lamps, and producers are saying there is a line, resonance line, it's emitted from this hollow cathode, and you need to survive with this, and nothing more about what hollow cathode emits. And hollow cathode, this has advantage. There's no limitation to volatility, because this atomization is by sputtering is very effective. Atoms are coming in plasma. No discharge produce atoms and ions. It's all very important. And of course, it's very broadly used. It's as a instrument for atomic spectroscopy, and we used to do it for decades. It's inductively coupled plasma, radio frequency is like 27 megahertz or 56 megahertz before. With industrial load frequencies, and you have such generator, you can produce excited atoms in some volume and get very intensive light in comparison with hollow cathode lamps. It's 10 to 100 times more intensive and very broad spectrum. And usually it's absolutely only atomic spectrum, nothing else. And it's really easy to identify, easy to study. But inductive coupled plasma are not sources which you can buy on the market. And therefore, because it's not easy to be produced in large series, and therefore still it's not used for absorption spectroscopy instrumentation. Yes, and okay, it's already told. And inductive coupled plasma, you can use closed volume like this. There is an inductor. You can use some light wire to go to the spectrometer, but you can use also a system attached to the vacuum system to change your volumes and to change pressure and investigate. There could be different sources of radio frequency plasma emission, but based on microelectronics and semiconductors. But also we use just for stability and to get more power. We're still using also lamps. Where is our innovation or even some game changing? We said, okay, if we are getting the hollow cathode and getting the atoms and ions in gaseous phase, for sure they are diffusing from this cathode somewhere in this volume. When you are putting this inductive coupled plasma inductor there, these atoms or ions are captured by this radio frequency field, and you are getting excitation by inductively coupled plasma. There is a real picture already on this. You see there is a hollow cathode. You need to look for this to see emission from, but you see this emission coming from inductively coupled plasma initiated by this inductor. And what we started with some commercially produced lamps. There's a hollow cathode lamp is powered as usually with some 20 milliamperes of power. And you are putting inductive coupled plasma, you can get amplification 10 to 20 times. And we started with boron, and we really were surprised that we are seeing boron resonance lines from hollow cathode. And then putting this, we are getting amplification up to 20 times. And then we produced of course, you need that you want to excite and to investigate highly volatile atoms, you need to more power on hollow cathode. Industrial powered lamps is very small power, current, about 20 millimeters. We build this from silica glass, based on our capacities to build a lot of very sophisticated instruments in glass and silica glass and connection supply from vacuum pumping with gas supply. There is electrodes, very large electrodes mounted in the silica glass geometry construction. There is a hollow cathode built interchangeable hollow cathode made from graphite. You can put hollow cathode with some filling, take away, put next one. There is possibility to pump. And then you are getting there is your looking window. There is for changing your sample in your hollow cathode. And this is our instrument we are not now going to use. And you had seen yesterday on this poster session, my very strong student team. I'm really thankful to all of them. Altogether, we made a lot of progress. They have now really chance that we will go ahead with a lot of investigations. Yes, so we told this once more. Then there is additionally, if suddenly you are not satisfied that this diffusion from hollow cathode is enough coming out, you can make some little small flow from argon flow, and you can make outcomes there. And you, by a flow, you are pushing more your ions and atoms out in hollow cathode. The another option, which was not up to now, we are first team in the world who had seen inductive coupled plasma effectively excited ions, mostly ions, and even for such very hard volatile elements like boron, Arnolds mentioned gadolinium, and so on. It's really surprising, but we are seeing ion lines. That means that when we are what we had done. Yeah, this is yesterday's poster. You had seen already that is for boron. This is for gadolinium, and this is for lead. For gadolinium, it's already in this micro construction about silica glass. For boron is used only industry-produced boron lamp, and we simply set this amplification. The same from lead. We also put it only took industry-produced. And then, of course, we can use this our construction and to put all elements what we need or need. Our astrophysicists will advise us what we need to investigate. Yes, of course. And there is if we can do this, it's a lot of possibility for applications to satisfy various demands. what we had before, Sune mentioned that we know selenium, tellurium. I am also always based on selenium and tellurium from my childhood. And considering tellurium, for example, there is a lot of lines in this diagram. And we had seen in inductively cathode plasma sources of tellurium all these lines. That means that we can provide for NIST, for these standards of spectral lines, a lot of information, simply investigating all these lines with distribution of intensity for each of us. We can make a lot of branching ratio studies, like from this level, there's 3 lines, there's 4 lines, and so on. The similar picture could be for other very hardly volatile atoms. And the same you can do for the ions. Never had done before for ions and branching studies, and it's now very easy to go with such a kind of approach. Yes, and of course, what is really advantage, and I tested already with my students team in this, is that it's very simple experiment. If you have in your disposal experience of managing glass blowing and so on, and vacuum technologies in glass and silica, you can do a lot. It's very simple methods, and you can demonstrate to young students. You are tasting atom. You are seeing each atom. You can to manipulate and so on. It's very attractive. Partly, but there's a lot of physics behind, basic physics, and a lot of applications afterwards. Yes, thank you very much.